Okay, so we are going to talk about the concepts behind point estimates. So a point estimate of a population characteristic is a single number that is based on sample data and represents a plausible value of the characteristic. Um, don't make that confuse you. Okay. Basically, you have to decide what is it that you're trying to find. Are you trying to estimate the mean? Are you trying to estimate the standard deviation? What is it that you're trying to do? Most of the time, okay, we're trying to estimate the mean. And so we want to use estimates from the sample that make sense to use. So like, let's say, we're trying to use the mean, okay? Well, to estimate that, we could use, any number of things. We could use X bar. That's the sample mean. That makes sense, right? If you're trying to measure the mean of something, why not use the sample mean? We could also use the median. The median is something that could also work. We could use a trimmed mean. We could use all sorts of things. What wouldn't make sense, would be like to use the range. Would the range of something give you an idea of what the mean is? Probably not. It doesn't really make sense to use. So that's all they're really getting at, is that if you're trying to estimate something, you need to pick something that makes sense, something plausible. Any of these three for the mean would make sense in different situations. And there are situations where you might want to use one or the other, and we're going to kind of talk about that. But the main thing is that a point estimate is just kind of an obvious, plausible solution for that. So if you're looking for a mean, you need to probably use some sort of mean, some sort of average that's going to help you figure that out. And if you're trying to figure out standard deviation, you need to use something that kind of uses variation to use that. So the idea is that there's this concept between biased statistics and unbiased. So a statistic whose mean value is equal to the value of the population characteristic being estimated is said to be unbiased. So if you are using the same type of statistic, then it's unbiased. Now, if you are not, it's said to be, or excuse me, if it's the same, it's unbiased. If you're using one and it's not the same, or if it's not unbiased, it's going to be biased. Now, biased statistics, they happen. Sometimes you have to use them. And there are cases where we definitely will use unbiased statistics. But so don't make that sound like you can't use them. It's just not the best possible thing. And sometimes you can't do anything. You can't do the best possible scenario. So that's the difference. One is that it's going to have the same value, and one is that it's not. If it's the same value, then it's going to be unbiased, and if it's a different value, then it's going to be biased. Okay, so if you're looking at some different statistics, so let's say we have an unbiased data, or if we have this different types of data. Well, look at part A. So our first distribution, our true value is here, right? And we have our statistic that we've done our sampling distribution for is here, right? It's very wide. This is obviously not a very good statistic. It's obviously biased highly, because we're nowhere near the center. This is not a good statistic. This is not something that you're going to want to use to help find or estimate what your population characteristic is. So this is a no-go. So this is bad. Now, for B, we see, okay, well, our true value is very close to the center of our distribution. We have a nice normal curve here. That's pretty good. That's kind of what we want. It doesn't necessarily have to be dead on, but over time it needs to about even out to be there. This may be a biased statistic, but it's a decent one. And that's okay, right? We can use biased statistics so long as that over time it tends to give us a decent approximation, a decent estimate of our mean. Now, this over here, we have a very tight curve, and we have our true values right about dead on. This I would say is very good, or a best case scenario. So this is a very good, even if the statistic is where happen to be biased in some way, it's obviously a very good bias statistic. So this is something that you want to use. We want a small standard deviation. If we're going to use bias statistics, we want as small as possible. So even though both of these are good, B and C are good, we want the best version. So if you were to pick a statistic to use to estimate based off these three, it would definitely be C, because it's very close to the mean value, and we also have a very, very low standard deviation. So you always want to go with the lowest standard deviation if you can. So that's what this is basically saying. If you have several unbiased statistics, you want to use the one with the smallest standard deviation. So just like the example before. So a couple of cases. So let's say if the population distribution is normal, then X bar has a smaller standard deviation than any other unbiased statistic for estimating the mean. So you could almost do a very small trimmed mean and it would still kind of work, but this would be the best possible scenario. Now, when the population distribution is symmetric, okay, so like if you have a symmetric distribution with heavy tails compared to the normal curve, so it's a little flatter than normal, a trimmed mean would be better than the true mean, because a trimmed mean would more than likely have a smaller standard deviation than something else. So this would be a way for us to say, okay, use something different than just your sample mean. So a trimmed mean could be better and is better when we have heavy tails. So so something like, this would be like a, normal, and this would be more like a heavy tail. So we've got bigger tails than we would normally have. It's a little bit flatter than usual.